Okay, so we started talking about forces last time, and we're going to be making a really big deal out of forces because this is what drives motion, and this is what people think of when they think of Newton and his laws of motion and how forces are related to motion. And the thing that we'll find out is that always, always, always we understand that there are really only two possible states, and this simplifies things so much, okay? And you'll have to keep reminding yourself of this, and eventually it'll become intuitive. But there's only two things that can happen. I'm either moving at a constant velocity, in which case there is what kind of a net force present? If I'm moving at a constant velocity. A zero net force, thank you. If there is a change in motion or acceleration, right? Those two things are synonymous, change in motion, acceleration. If there's a change in motion, then there is a net force. There are only those two possible things, okay? So, if the net force is acting on an object is zero, the object is said to be in equilibrium, and it will remain at a constant velocity. If the net force acting on an object is not zero, the object will change its motion. It will accelerate. So, we're in a position then to start talking about Newton's second law. Newton's first law says everything resists change in motion. Everything wants to be in constant motion. If it's a constant motion is zero, that's fine, but everything wants to be in a constant motion, and everything will resist a change in that motion. But if I do have a change in motion, how much will that change in motion be? And we've said that that will depend on how much the net force is. The greater the net force, the greater the acceleration. And I tried to point out to you that we all could have been Isaac Newton. We could have all come up with this same observation. The greater the net force, the greater the acceleration. We see it every day in our lives, right? Also, we could have been Newton. We know that the greater the mass, the less the acceleration. The greater the mass, the less the acceleration. So, Newton's first law says objects resist a change in motion, but if you do change the motion, it needs a net force. Newton's second law says how much force. So according to Newton's first law, if there is no net force, the velocity will not change. But if there is a net force, the velocity will change. The next question is, how much will it accelerate for a specific amount of force? And I'm trying to make sure you understand that this is an intuitive thing. We see it every day. If I push a bowling ball softly, the bowling ball that we're talking about, will the amount of acceleration be less or greater than it? Did we do this already? No. Okay. Will the amount of acceleration be less or greater than if I push the bowling ball harder? Less. Okay? I know it seems obvious, but the more we say it, therefore the acceleration is proportional. Okay? The acceleration is proportional to the force applied. Or we use this cute little symbol here. It almost looks kind of like a Greek alpha. An open kind of an infinity sign. It's not quite an infinity sign either. But this symbol means that it's proportional to the force. If the outcome and the input increase or decrease in the same direction, then it's said to be directly proportional. Okay, so if I increase the force and I increase the acceleration, that's directly proportional. Right? If they occur in the opposite direction, they're said to be what? Inversely proportional. So if I increase the mass, but that decreases the acceleration, that's an inverse relationship. Okay? And we've already answered this. What else might the acceleration of an object be proportional to? We've already said the mass. And we've already said that it would be inversely proportional to the mass. We kind of got ahead of ourselves, right? Because we've already said this. Because acceleration is inversely proportional to mass, would a 16-pound bowling ball have a tendency to resist acceleration more or less than a 12-pound bowling ball? Which is going to resist acceleration more, the 16-pound ball or the 12-pound ball? 12-pound ball. The 16-pound ball. Right? It's got more mass. Mass. It's got more mass. So it's got greater inertia. It's going to resist. And so we've said this again too already. The tendency of an object to resist acceleration is called what? Inertia. Inertia, thank you. Okay? Hopefully we've got that. Why am I dropping those? Okay, so now just by thinking about it a little bit, we can derive Newton's second law of motion. Our understanding, at least of that aspect of what Newton did, is just as great as anyone else's. Okay? Our brains can see this intuitively just the way Newton did. Okay? The acceleration of a quantity of matter is directly proportional to the net force on it, inversely proportional to the mass, or the more famous statement of Newton's second law is just force equals mass times acceleration. Okay? Now, what would the units of force be? And you should already be able to figure this out even without us kind of going through this. If I know that it's mass times acceleration, what do I measure mass in? Kilograms, right? That's what we've always measured mass in, kilograms. And I know that acceleration is meters per second squared, right? So, kilogram meters per second squared. You should never not be able to tell me what the units of force are. Yes, they are newtons, but I want you to know that they're kilogram meters per second squared, and it's easy to figure that out. Even in your brain, you can go mass times acceleration, kilograms times meters per second squared. Okay? And that's a newton. Now, we made a big deal out of our motion efforts in drawing diagrams. We said that for motion problems, the purpose of the motion diagram, or the purpose of our diagrams, is to make sure we capture all the information. We don't forget anything. And once we have all that information, then we can figure out how to solve the problem. It's going to be the same way with forces. So in order to be able to work problems involving forces, it'll be critical for you to be able to visualize the blank to which forces are applied. And we said that we're going to call our object the system. Right? And then we said, very simply, the environment or the surroundings in which these forces are acting. And then, more importantly than any of that, is the direction from which the forces are applied. And I've got direction in there a second time. So scratch that out there, because that's what I want. To accomplish this, we can create a variety of diagrams. Now, I won't ask you to necessarily draw a pictorial model for everything that we do. A pictorial model is simply a simple sketch of the system in which the forces are acting. It doesn't have to be a masterpiece, but it does need to be neat enough to clearly display what's going on. Complex objects like cars, people, animals, rocket ships, etc. can be simplified to geometric shapes, roughly resembling whatever the object is. The simpler the better, and the less time you'll spend. This doesn't require any artistic ability. In general, we won't draw a pictorial model unless we absolutely have to, because it takes a little bit of time and effort. They take up time and space. So if you need a simple sketch of something to help you figure it out, that's fine. More importantly will be something that we're going to call the free body diagram. And a free body is basically a dot. Free body diagram will be our method of visualizing forces acting upon the system. We'll start by representing the system with a dot. Then we'll draw one or more arrows extending from the dot, representing all the contact forces that are acting on the system. The lengths of the arrows should be proportional to the magnitude of the forces. In other words, if this arrow represents 5 newtons, then a 10 newton arrow should be twice as long. Okay? Now, I'm not going to get bent out of shape if it's 1 3/4 time as long or 1 5/8 time as long. I'm not going to get a ruler out and measure it or anything like that. But it should at least be longer. The longer the greater the force, the longer the arrow should be. Okay, can I get one of you guys to shut that door for me? Okay, the direction of the arrow should represent the direction of the force, and we're going to have to label these appropriately, as we always do. Then we're going to do the same for any long-range forces. The only long-range force we have at this time is gravity. Now, I don't really care which you put down first. You can write down the contact forces first and then the long-range forces, or you can write down the long-range forces first and then the contact forces, or you can kind of mix them up. It just depends on which your brain thinks about first. Then, if room is present, include the formulas in the labels and perform calculations on the diagram. That won't happen very often. Most of our diagrams will be a little bit more complex, and if you start putting formulas and calculations on the diagram, then it'll clutter it up to the point where it's not very useful. Then, visualizing the relative lengths of the arrows for these various forces. And we're going to scratch this part out because I'm not sure why I haven't taken it out before. Draw an arrow that you think will represent the net force. And I don't want to do that because that just clutters things up too much. Okay? If there's no acceleration, then the net force must be 0, and the net force can be represented by a dot. Again, we're not going to draw in a net force, so this whole last part of the paragraph should be taken out. Okay? And in fact, I think I'm just going to eliminate it right now so that I don't have to say that again next year. Okay. Constructing an accompanying motion diagram may or may not be necessary depending on the situation. Now, I've said for the time being we will do so regardless of whether or not there's any motion, unless information about motion is not provided with the problem. Begin by drawing your coordinate system adjacent to the pictorial model or the free body diagram so that the x and y values clearly represent the directions of positive value, just like we always write a motion diagram. Then, as we previously have done, indicate the motion of the object and label given information. And if there is no motion, velocity and acceleration can be indicated by dots. Okay, so we're going to practice this idea a little bit, and we're only going to deal with free body diagrams for the time being. Okay, we're going to spend a little bit of time practicing this. I'm going to demonstrate a couple of these, and then you're going to do some of these on your own here in class. Okay, a skydiver falls downward through the air at a constant velocity. A skydiver falls down through the air at a constant velocity. What contact forces are present in this scenario? If I'm falling down through the air at a constant velocity, I'm not accelerating. What contact forces must be present on the skydiver? Yeah.
And resistance?
Okay, so all the particles in the atmosphere, right? They're smacking up against the skydiver coming down. And what would the direction of the force be on the skydiver as he's falling down through the atmosphere? What would the direction of the particles on the skydiver be? What's that? Yeah, they're pushing him upwards, right? So I've got a force in the upward direction. Okay? So we're going to say air friction, or you can call it air drag. Doesn't matter. We're going to label this force of the air. Okay? Doesn't matter to me if you said air drag here or air friction or just air. You just need to label it some way so that I know what you're talking about. Okay, if you just put F there, that doesn't tell me that you understand what's causing that force. What non-contact force is present? Okay? Now, I have to make a decision here. I want this to represent my forces accurately. Which of those two forces has to be greater? Okay, wait a minute. Think about the scenario. What's it say the velocity is? It's constant. What are the circumstances surrounding a constant velocity? Do I have a net force on the object, or do I not have a net force on the object? I don't have a net force on the object. The object is traveling at a constant velocity, and that tells me I have balanced forces. Therefore, the force due to gravity, little fg, has to be the same in the downward direction. Neither force is greater. Forces must be balanced. Okay? Now, why is that uncomfortable for me? I've been doing this for years, and it's still uncomfortable for me. Why is it uncomfortable that we're saying these two forces have to be the same? The force upward has to be the same as the force downward. Why does that bother us? He's falling down. Okay? But he's falling down at a constant velocity. Balanced forces does not mean the object is not moving. He obviously doesn't just stop in the middle of the atmosphere. Balanced forces means they are not accelerating. Okay? So, if I have a constant velocity, even if it seems this is ridiculous, he's moving downward, there must be a greater force downward, it's not true. The forces are balanced at that point. What do we call it when the forces become balanced on a skydiver and they're now traveling at a constant velocity? What do we call that velocity? It's terminal velocity, right? Okay. So draw the free body diagram, including the formulas for the force due to gravity. Okay, so I can do this. I know that the force due to gravity is mass times the acceleration due to gravity. Force equals ma, right? And in this case, the acceleration related to the force due to gravity is the acceleration due to gravity, and we call that little g. And what have we said that acceleration is? Negative what?
9.8.
9.8 meters per second squared, right? That's what that acceleration is. And if I multiply the mass times that acceleration, I get the force with which gravity is pulling down on that person. Okay? Force equals mass times acceleration. In this case, the acceleration that we're talking about is the acceleration due to gravity, which in and of itself kind of bothers us because we're saying, hey, there's an acceleration here. But yet we're traveling at a constant velocity. We would be accelerating, except there's a force acting on us in the upward direction too, right? Okay. Now, let's add some numbers into this. Given that the mass of the skydiver is 117 grams and the force of air resistance is 36 newtons, create a problem that illustrates how far the skydiver will fall in 13 seconds. Okay? Given that the mass of the skydiver is 117 kilograms and the force of air resistance is 36 newtons, create a problem that illustrates how far the skydiver will fall in 13 seconds. Is how far the skydiver will fall a motion thing or a force thing? How far they'll fall. Is that a motion thing or a force thing?
Motion.
It's a motion thing. Okay? So if I'm going to create a problem that talks about this, I'm going to need to create some kind of a motion problem. Okay? Now, the way that I'm going to think about this is I've been told that they're going at a constant velocity. So do I know a motion formula that will tell me how far they're going at a constant velocity? Remember our 5 formulas. I have x equals x0 plus vt. I have x equals x0 plus v0 times time plus 1/2 at squared. I have x equals x0 plus 1/2 v plus v0 times time. I have v equals v0 plus at, and I have v squared equals v0 squared plus 2a times x minus x0. Now, remember when we talked about motion problems, we had our list of questions, right? My first question is, do I have time or do I not have time? Do I have time in my scenario? Yes, so I can't use that formula. Never mind that it requires acceleration. My second question was, do I have constant velocity or an acceleration? And we have constant velocity, and we said that my second question related to this first formula. So I go from here up to here, and since I have a constant velocity, I'm going to have to use that. Okay, in order to figure out how far I go in 13 seconds. Okay? In order to figure out how far I go in 13 seconds, I'm going to say x equals x0 plus velocity times time. Okay? Now, I've kind of made a problem for myself here. because given this scenario, I'm not going to be traveling at a constant velocity. Okay, so I need to back up for a second. I kind of forgot how this problem was going to work. I apologize.
It's okay.
Let's scratch that out too. Okay, what I forgot was that when I said, okay, now let's do this scenario, that this scenario kind of voided what was going on up here. So let's pretend that part of the last 5 minutes of our discussion just focuses on now the fact that I might be accelerating. Okay? So let's take this scenario and start over again and see if we're going to have the same thought process. And let's look at the force due to gravity here first. Force due to gravity equals mg. What's this guy's mass? What's the guy's mass? 117 kilograms. Okay? What's the acceleration due to gravity? 9.8 meters per second squared. So can I get somebody to calculate what 117 times 9.8 is?
$1,146.
1,146?
Yep, 0.6.
Okay, well, let's say 147 then. 1,147 newtons. Okay? So gravity is pulling downward on me with a force of 1,147 newtons. And that's not going to change, is it? I'm not going to change my mass at any point in the fall there, so that gravity is not going to change. What have I said the force of air resistance is, though? In this case, force air equals what? What's it say? 36 newtons. Okay, so clearly in this scenario, not this scenario up here, clearly in this scenario, I've got a much greater force in the downward direction than I do in the upward direction, so it's not balanced. Okay, now we've got a scenario where it's not balanced. Okay, and so we're not going to be dealing with that situation. We're going to be dealing with this new situation. Okay, and that means that this is going to be accelerating. But I have been given a time. So I can't use this. I've been told now that this is an accelerating circumstance, so I'm not going to be able to use this. I haven't been given either an initial or a final velocity, so I can't use this. And the instant that I jump out of an airplane, what's my velocity going to be? 0. So we're going to say that this is like the instant that I jump out of an airplane. And when I do that, I'm immediately going to have a little bit of air resistance, but not much yet. And so we're going to say our initial velocity is 0. But we don't know what our acceleration is going to be, because it's going to be less than 9.8 meters per second, right? It's going to be the sum of this and this. One of these is in the positive direction, one's in the negative direction. So I'm going to have to find out what the acceleration is related to this minus this in the opposite direction. So how do we go about doing that? So I'm going to need to figure out what the acceleration is. But I'm going to start by writing down x equals x0 plus v0 times time plus 1/2 at squared. And I'm going to say this drops out. And I'm going to say my 0 point, we're going to say is 0. And then we're going to say x is how far I fall. So x is going to equal 1/2 at squared. But I don't know what a is. Okay? And I can't use anything else to help me find a. So in this case, I'm going to have to use a force problem to help me solve the motion problem. So here's what we do. When I have a force problem and I've drawn my free body diagram, I always draw my free body diagram first so I can see what the forces are. Then I need to find out what the net force is. So I'm going to write down net force. Now, I only have two possibilities. Either the net force is 0 if the forces are balanced, which is not the case here, or the net force equals what formula? Force equals mass times acceleration. So when I write these things down, I write a free body diagram and then I say net force equals. If I have no acceleration, I'll say 0 newtons. If I have an acceleration, I'll say mass times acceleration, because this is how we're going to figure out what acceleration is. And then, not only does net force equal mass times acceleration, it equals the sum of the forces. That's what net means, the sum of, or the combination of. And what we're going to do, our practice is going to be, is we're going to not give positive or negative values to our forces. We're going to say all of our forces are positive. This one happens to be positive in the negative direction, and this value would be positive in the positive direction. But don't worry about that. We're going to make our forces all be absolute values, and we're going to use our free body diagram to say which one gets subtracted from which. Which one of these values is far greater? Gravity. So in order for me to figure out what the net force is, I'm going to have to subtract this force, which is in the opposite direction, from this. So I'm going to say force due to gravity minus force of air resistance equals 1147 newtons minus 36 newtons, and that's going to equal 1111 newtons.
Yep.
Okay? Now I have a formula I can use. I need to find acceleration. So in order to find acceleration, doesn't it make sense that all I need to do is divide this by mass? Okay, so we're going to say acceleration equals 1100 newtons divided by 117 kilograms. And if somebody could figure out what that is.
9.49.
9.49.
That's 9.5.
So 9.5 meters per second squared. Okay? Now I can go back in and figure out how far I fell. X equals 1/2 times 9.5 meters per second squared times 13 seconds squared I'm going to get these out of the way here.
We can't erase that like you can Dr. March.
I'm sorry. Draw an arrow to somewhere else where you can write the answer. So 1/2 times 9.5 times 13 squared is what?
What you want?
What was the
I'm
question?
sorry?
What did you ask?
I said 1/2 times 9.5 times 13 squared is what?
802.388.
802 meters. Okay, so during that time, they fell 802 meters. Okay, so our pattern of activity, free body diagram, net force equation. If the motion is not accelerated, force net equals 0. If the motion is accelerated, net force equals ma. I only have two possibilities. Sorry about that. I closed my computer up. No, that's not a sign. Okay. So let's try another one, and then I'm going to ask you to see if you can try to work on one of these by yourself. Okay, a cable pulls a crate at constant speed across a horizontal surface. There is friction. What contact forces are present here?
Friction.
Friction would be one of them. Okay, and we're going to call that an applied force. Okay, the force of, or actually we're going to call that tension. A cable pulls a crate, we're going to call that tension. There's one other applied force here. Or one other contact force.
Air resistance?
Nope, we're not going to consider air resistance. No. Is the box falling through space? So what other force is there?
Gravity.
Okay, but that's not a contact force. What's keeping it from falling through space? It's on a surface, isn't it? And isn't the surface applying an upward force on it? What did we call that force? We called it the normal force, right? If I have a surface and it applies an upward force on something, the word normal implies perpendicular, and we said that that's the normal force. Okay? So the normal force is the force of the surface pushing up on the box. And we've already said that the non-contact force present is gravity. Okay? So I can start writing these forces down. I know that the box is not accelerating in an up or down direction, is it? Therefore, I know that the force due to gravity and the normal force have to be balanced. In that direction, in the vertical direction, there is no acceleration. So these two things have to be balanced. Okay? I have an applied force or a force due to tension. how long am I going to make my friction arrow in the opposite direction? Why am I going to make it the same length?
Because
Because it's at a what velocity? It's at a constant velocity, right? There's a constant velocity there. So again, it doesn't mean that these things are not moving. It just means they're not accelerating. And a lot of people are going to get really confused by this because, hey, if I'm pulling on the box with a force of tension and the force of friction is the same in the opposite direction, that box ain't moving. Well, it could be moving. It's just moving at a constant velocity. Okay? It's not accelerating. Which force is greater? None of these. Gravity and normal force are balanced, and, bless you, force tension and friction force are balanced. I'm going to look and see what my problem is here before I make the same mistake I made last time. Okay, I've got my free body diagram. And I've been told that the force of friction is going to be 24 newtons. So I want to find out what the strength of my applied force is. Okay, now you can already see just by looking at this, if my force of friction is 24 newtons and it's balanced with the force of tension, your brain should automatically tell you that the force of tension is also 24 newtons, right? They're balanced. But let's prove it. You have to show me that. First thing I always do after creating my free body diagram is write down a net force equation. Force net. In this case, forces are balanced. There is no acceleration. And under that circumstance, I write down 0 newtons. Okay? I don't write down MA this time because there's no acceleration. Again, there are only 2 things that you can write down after you write down force net. You can either write down 0 if there are balanced forces, or you can write down MA if there are not balanced forces. This will be an always thing. Okay, because this is how you're going to figure out how to solve the problem. So, you'll write down force net first, then you'll write down either 0 or MA, and then you will write down the sum of forces. And if my forces are balanced, it doesn't really matter which one I put first and then which one I subtract from the other one. But I tend to go in that circumstance with whichever one's going in a positive direction. So I'm going to say that my sum of forces is force of tension minus force of friction. Force of tension minus force of friction. But you could have said force of friction minus force of tension if you wanted to. Now, you might be confused by the fact that I'm saying sum of forces, when in fact I'm subtracting. Okay? If you want to, you can think of this as force of tension plus the opposite of the force due to friction. That makes it a sum, right? Okay? And the reason that I'm doing this, both of these imply, bless you, that I'm subtracting something in the opposite direction from something in the positive direction, right? I'm subtracting this from this because they're in the opposite direction. We're letting this formula put a sign on our forces here. We're going to always have forces be an absolute value or a positive value. But then we're going to use the direction of these forces to say which thing gets subtracted from which thing. Okay? And now that I've got this, I can see that if this is 0 newtons, then in order to figure this out, I'm going to add force of friction to the opposite side. And that then becomes force of friction equals force of tension, right? All I did was just add force of friction to this side because this is 0, and I can just add that to 0. And then I can say force of tension equals 24 newtons. Okay? Now, I understand that you might think that it's silly that when I can immediately see what my force of friction is going to be, or it's 24 newtons, I can immediately see that the force of tension also has to be 24 newtons. Why do I have to show that? You're always going to have to show or prove to me that you understand the math that goes behind your reasoning. Okay? Any questions about that one? Okay, I'm going to do one more just because it's weird, and then you're going to work on the other two by yourself. Okay, a rope lifts a bucket upward at a constant speed. Ignore air drag. What contact force or forces is there or are there?
Tension.
Tension. And what non-contact force?
Yeah.
Gravity. Which force is greater? Neither. We've learned it, right? We've figured it out. If I'm traveling at a constant velocity, neither force is greater. Force due to gravity equals force of tension. Okay? Tension in the rope is 154 newtons. I can put that on my thing here, my diagram. And I can also say that the force due to gravity equals mg. And if I wanted to, I could probably also say that since these are balanced, the force due to gravity must be 154 newtons. But I'm not asked what the force of gravity is here, am I? I'm asked to figure out what the mass of the bucket is. So, assuming that I don't know how to solve this problem, I'm going to let my strategy lead me through it. What's the first thing I write down now? F net. Okay? I could either write down 0 newtons or MA next. Which of those am I going to write down next?
0 newtons.
Okay? Because it's traveling at a constant speed. Okay? And then I'm going to say this equals, and I'm going to put force of tension first. It doesn't really matter. Force of tension minus force due to gravity. And then I'm going to say, because I can, that this equals force of tension minus mg. Okay? And now, since I know that this is 0, I'm going to add mg to the opposite side of the equation. And it's going to say mg equals force of tension. And then because I want mass, I'm going to isolate mass and say that mass equals force of tension divided by acceleration due to gravity. And then I'm going to say 154 newtons divided by 9.8 meters per second squared. If somebody could divide 154 by 9.8 for me, I'd appreciate it. What'd you get, Kirsten?
15.7.
15.7 kilograms. So the bucket must weigh or have a mass of 15.7 kilograms. Now, I've got newtons over here divided by meters per second squared, and I just want to make sure you understand how I know I'm going to get kilograms here when I divide newtons by meters per second squared. Remember again that newtons is the same thing as mass times acceleration, which is the same thing as kilograms times meters per second squared. And so this is the same thing as saying kilogram meters per second squared divided by meters per second squared. Right? Meters per second squared cancel out, leaving me with kilograms. Okay? Any questions about this one? Okay? I'm going to let you guys work on the others, and then we'll see if we can come back and then put those together. Just a kind of a hint here. A rope lowers a bucket at a constant speed. Ignore air drag. And the point of that one is going to be so that you can try to understand how it's possible that the same forces are present for both bucket scenarios. But go ahead and see if you can do that one and then the rocket one as well. So I'm going to give you the next 10 minutes to work on those. And see, and you can certainly work together.